Okay, so what I want to do this time is finish up very briefly what we said last time. So last time we calculated the spectrum of scalar perturbation. I'm going to show you how very quickly the calculation for tensors is basically the same. Yeah? So it just needs a few steps to actually show that the action that you get for tensor fluctuations is just 2 copies of the scalar action without this extra conversion factor, and then so you get the same, you get part of the same power spectrum. So you don't have to do the calculation again. And in fact, there's a reason that tensor fluctuations are much simpler to calculate. So sometimes people actually present that one first. And there are 2 reasons why tensors are simpler. One is that they're gauge invariant. So we don't have to massage things into a way of getting this curly R co-moving curvature perturbation. So that makes it simple. And then the other thing that makes it simple is that fluctuations in the tensors don't backreact on the energy density. Yeah? So when we were calculating these scalar fluctuations, whenever the scalar was fluctuating, it was changing the inflationary energy density by a little bit. And we had to keep track of that backreaction onto the total matter density. Whereas tensors are basically just a spectator field, that don't significantly backreact on the geometry. So you can basically just calculate them in a fixed background rather than having to worry about interactions between fluctuations and metric perturbations and matter perturbations all at the same time. So there's something to be said about just doing tensors separately first, but I decided to do the other way around. Okay, so let me just remind you of our favorite diagram. So I'm going to draw this until you're truly sick of it. So this is just the co-moving Hubble radius as a function of scale factor. Or conformal time. And so if I put minus infinity here, 0 here, and then positive values, and specifically the value today, here at this end, then we know we have inflation when this co-moving Hubble radius is decreasing. And then we have what I call the hot Big Bang, and by that I just mean conventional FRW expansion after reheating. So reheating is happening around here. And so you have this qualitative feature that you have a shrinking co-moving Hubble sphere, and then you have an expanding co-moving Hubble sphere. And that means if you look at a co-moving fluctuation, so this is k to the minus 1, a wavelength of density fluctuation or fluctuation in this co-moving curvature perturbation. So then what we did last time is we basically calculated the power spectrum at this point. Yeah, so when the mode first exits the horizon. So the mode starts its life deep inside the horizon. So that is sub-horizon. Then it becomes super-horizon. And here it becomes sub-horizon again. And so the way we calculated this is by setting boundary conditions when the mode was deep inside the horizon, when it basically feels as if it's living in Minkowski space. Yeah, so it doesn't really see the curvature, the horizon scale of the universe. And it's just imagine, locally it just feels Minkowski space. And so you can, arrange for preferred boundary conditions, that basically descend, just from having boundary conditions on these Minkowski wave functions. So that's why we set these initial state boundary conditions at minus infinity or anywhere deep inside the horizon, some early time. Then we calculated this. So then most of today's lecture, after I finish talking about tensors, is going to be what happens once the mode comes back inside the horizon. Yeah? So I told you this quantity R is nice because outside of the horizon we proved, or I asserted, that the time derivative is approximately 0 as soon as this mode goes outside the horizon. So I basically can just translate this result from here to here without doing any work because I know it stays the same. Yeah?
Would there be modes which would just go under, never go?
Sorry?
Would there be some modes which would just go under?
Oh, under here? In principle, yeah. Yeah. I mean, those would basically modes that would still be sub-horizon all the time. And they would never be classical modes. They would always be like quantum fluctuations. But yeah, I should say, I'm drawing, so scales are increasing this way, yeah? Co-moving scales. So I could draw, if I want to draw a couple of perturbation modes, larger scales are further to the top of this plot than smaller scales further. So the further down I go, the smaller scales I'm considering. And I could be considering smalls that are much smaller than the horizon size at reheating, but that's very small. Okay. So one thing we could check from this picture, for example, and then so the CMB would say, let's imagine the CMB is here. And today's horizon is somewhere is here. Yeah, so this is not really to scale. It's hard to draw this to scale. If you ever try drawing this to scale, it looks a little bit squeezed up. So we have the CMB decoupling here, and then we receive the CMB photons coming from this region. Yeah? So when you look at the CMB power spectrum, you see, of course, something like this. So let's imagine, for example, these three different modes. Mode number A, B, and C. Yeah? So this is a mode that exits the horizon just at CMB, or re-enters the horizon just at CMB decoupling. So on this plot, this would correspond to somewhere around the first peak. Yeah? And so anything to the left of the first peak is sub-horizon at recombination. And everything to the right, and everything to the left is super-horizon at recombination. So for example, this other mode here, this mode A, just entered the horizon today. So it's something like the quadrupole moment, the dipole. And it was outside of the horizon at this time when the CMB was released. Yeah? So this mode A would be somewhere here on this plot. And then this mode B, which was inside the horizon when the CMB was released, would correspond to something to the right. Yeah? So I think it's worth understanding this matching. Then you see how these different modes correspond to different scales. Yeah? Okay, so what I'm going to talk, most of my time today, I'm going to talk about this transfer. What happens when the mode comes inside the horizon, gets re-expressed as temperature fluctuations in the CMB, and then here, temperature fluctuations here. And then those temperature fluctuations are projected to us today. So when we look at the sky, there are projection effects that make this, a harmonic space function rather than, k-space, for example. So you do need to do some projections with Bessel functions and things like this. So I'm going to explain these two transfers. One, how to relate perturbations in R to perturbations in the CMB temperature, and then how to relate those CMB temperature fluctuations in what we actually see. Yeah? Okay. And just to remind you of the final result from last time, so the spectrum of scalar fluctuations, which was defined as k cubed over this 2 pi squared, the power spectrum of this curvature fluctuation. And this 2 pi squared, actually, I explained in the appendix, depends on your Fourier conventions. I got this wrong a couple of times until until I stopped being stupid. But so you can figure out where you put your 2 pi's in the Fourier conventions and then define the power spectrum as the Fourier transform of the 2-point correlation function. That actually affects whether you have some coefficients here. But okay. So this is the result that we want to remember. So we had h over 2 pi squared. Yeah? So this is one of the most famous results that we have in this business. Yeah?
Sorry. In the lower line, where exactly is the k from this?
Good. So this comes because this is supposed to be evaluated at horizon exit when k is equal to AH. Yeah? And that's precisely, actually, so last time actually, at the very end I calculated this in the perfect de Sitter limit. Yeah? Where actually there was no real time dependence in this, in H or in even, yeah? But the way you then sneak in time dependence is that you say you evaluate this at horizon exit, and horizon exit would have a slightly different value of H if you evaluate it at different times. So that's where the time dependence gets sneaked in. There's also a difference. So I actually give you an exercise at the end of the second lecture where you actually I walk you through how to do this in like an expansion in slow roll parameters, where you sneak in the time dependence in a slightly more systematic way. But here it's effectively saying whenever the mode exits the horizon, it seems as if it's just in static de Sitter space, determined by just a constant value of H. And then you just basically adiabatically change this value of H for different modes, you exit the horizon at slightly different times. And H changes. Yeah?
5 bar dot is also
Sorry?
5 bar dot is also going to be different.
Also changes. So this actually can be written as something like H squared over epsilon. Yeah? If you look, our definition of epsilon was something like this. H dot over H squared, or 1/2 phi dot over H squared. Yeah? So this power spectrum is proportional to H squared over epsilon. Yeah? So then the magnitude of these scalar fluctuations depends on both the Hubble scale, or the energy scale during inflation, and the shape of the potential, or the flatness of the potential. So there's this degeneracy, you can't, yeah, it depends on both of these parameters, so it gives you information about both combined rather than separately. Yeah? And of course, one thing that we're going to talk about is that we know this amplitude. So roughly this is 10 to the minus 10. This is something we have to match. We know that has to be true, because otherwise we can't. So you have to start with this magnitude of fluctuations to explain why we have galaxies, with a certain density contrast delta today. So you can basically then take this initial condition, do some numerical simulation, and evolve those fluctuations forward. The fluctuations will clump under gravity. And in order for them to clump sufficiently fast, you need an amplitude that is of this size. Or if it was any bigger, it would be clumping too quickly. So this is one of the basic things we always have to match, this amplitude of scalar fluctuations.
So this is only at scales of horizon scales?
This?
I mean, the whole thing. So
Yeah, so actually, I'm going to talk about the scale dependence of the scalar spectrum
okay.
in 10, 15 minutes.
Okay, so you're not really looking at the K dependence of this at all.
We will eventually, and we will see that it's very weakly K-dependent. Basically, one of the famous results is going to be that it's almost completely independent of scale, nearly scale invariant. Any breaking of scale invariance is just proportional to slow roll. So the fact that inflation happened and happened, with small slow roll parameters tells you that the spectrum is very nearly constant in K.
So that number tells me the height of the heat.
Sorry?
So that thing over there tells me the height of the heat at B only?
No. So good. So inflation predicts something very boring. So when we talk about the scale dependence, we're going to predict that this delta S of K looks like this. Yeah? Or maybe like this. Yeah? Maybe a little bit tilted. So really what's happening is we have to understand these transfers. Yeah? So when I told you I have to relate this curvature perturbation R to delta T, and then delta T gets projected, all of that convolutes to make this look more interesting. But actually, my main goal is to explain to you this transfer and then tell you that we understand it well enough so that we can calculate backwards and say, inflation produced something like this. So really, we want to solve the inverse problem of going from observations that look like this to just the primordial spectrum. Yeah? So I'm going to explain to you how that is done. Yeah? Okay, so yeah.
what's not the slope of these two lines in reality?
Sorry?
The slope
Yeah.
of these two lines in reality. How they go? Are they really 45 degrees or?
Oh, these?
Yes.
So I'm plugging this as a function of log A. And that's why it's linear. Yeah. So you can think about it. So just think about. Let's do one example. During matter domination, for example, you can ask, AH to the minus 1. How does it evolve with scale factor? So during matter domination, H squared goes as A to the minus 3. Yeah. So then this goes as like A times A to the minus 3 halves to the minus 1. So A to the 1/2, yeah? So this would have, during matter domination, this would have a slope of 1/2. During radiation, I think it then would probably have slope A, 1. So I drew this a straight line. Actually, it really should be changing when you change from radiation to matter. And during inflation, H is constant, roughly. So it goes like A to the minus 1, so it has slope minus 1. So it's minus 1. Then it goes to radiation, it's minus 1. And then it goes to 1/2. And then during dark energy domination, you can figure out it's probably just minus 1 again. Yeah? Okay. Okay, so let me just sketch out how this calculation works for tensors. I think I learned my lesson of not writing too much. So tensor fluctuations, of course, I described was are these transverse and traceless metric perturbations. Yeah? And so in Fourier space, I can write them as an integral over k. Then here I want to sum over two polarization modes. I introduce this polarization tensor, HK. Yeah? And so this polarization tensor has to satisfy a couple of properties. So it has to be traceless and transverse. So it should be annihilated when you hit it with a Ki momentum vector. And then if you take the inner product of two of these polarization modes, you normalize it like this. Yeah? And this factor of 2 is different people have different conventions for that. Yeah? I want to keep everything. Yeah. I don't know. Okay, so and then actually, so the action for the tensor perturbation comes purely from the Einstein-Hilbert action. So this, and now let me introduce the Planck mass, because here we want to keep track of dimensions a little bit more carefully. So I just start with the action for gravity, yeah? And you expand this to second order in perturbations of the metric. Change to conformal time. So this is just the standard second order action for metric perturbations or gravity waves, basically. So if you were to vary this with respect to Hij, you just get a wave equation for these metric perturbations. And so now in terms of these Fourier modes, what I would find is, so delta S2 would be a sum of the two polarizations. And here the integral over, now this is an integral over k. So my primes, again, are derivatives with respect to conformal time. Squared. Okay? And now this parameter v is just a rescaled version of the metric perturbation. So it has one factor of the scale factor. It has an m Planck and then h to the k, hk. Yes. So this v here is analogous to our Mukhanov variable that we had last time. So that's why I name it the same way. And here we have like a double prime over a, which you might remember last time we had this function z double prime over z. And during the zeta, it was actually approximately a double prime over a. So here, during the zeta, this is also 2 over tau squared. So you will recognize this is just 2 copies, basically, here for each of the polarization modes. 2 copies of the action that we had last time. Yeah? So then now we're done. Yeah? There's no quantization will work exactly the same way. Yeah? You just repeat the the thing, and you just keep track of how many copies you have. So there will be a factor of 2 in the final power spectrum if you want to add up the 2 polarization modes. There's a normalization here, an M Planck over 2, that is extra when you convert this. And so that will only change. So let me then just give you the final answer. So the power spectrum for tensors is defined, again, this k cubed over 2 pi squared. Now power spectrum of H. And I'm sneaking in a factor of 2. Because if I call this the power spectrum of each of these polarization modes independently. And then so what you find is 8 over M Planck squared. H over 2 pi squared. Yeah? So the H over the 2 pi are exactly the same. Those are basically the identical power spectrum that we calculated last time. And then the 8 over M Planck squared is because I have an M Planck over 2 here. So this one inverted and squared gives us 4. And then a factor of 2 because I have 2 polarizations. Yeah? So okay. So this is the reward you get after you suffer through scalars. The tensors are just like, you write down the answer almost immediately. Yeah? Okay, any questions on this? Yeah?
You don't have this factor of H over pi dot squared?
Exactly, yeah. Because last time, remember, there was this relation between, so V was actually equal to like Z times R. And this Z here was proportional to pi dot over H or something. That was this conversion factor. And so what is identical is the power spectrum for V. But then there's this extra factor here, which has this conversion from basically fluctuations in the inflaton field to fluctuations in curvature, if you want to think about it that way. And here there is no such thing. This is just, the only conversion factors are like constants. Yeah, Planck mass, factors of 2. This A was also common to both. Yeah. And physically, it basically has to do with the fact that scalar fluctuations backreact on the geometry. So there's this conversion, whereas tensors don't. Yeah? So this power spectrum here is actually universal for any light degree of freedom during inflation that doesn't affect the energy density significantly. Yeah? So if you have more than one field during inflation, it will always get a power spectrum that looks like this. Yeah? So that's important sometimes. And these metric perturbations or gravity waves are of course something that's not optional. This is just part of gravity. Okay. Okay, so there's then, just looking at these power spectra, there's a very simple observation you can make, and if you made that 10 years ago, you would be famous. And I'm going to show you how it really takes 2 lines. And even today, we keep talking about this relation. It's something called the light bond. And I'm going to talk about it more tomorrow. And so what people often do is they normalize the tensor perturbations with respect to the scalars. Yeah, so that they find this quantity R, which is called the tensor to scalar ratio. And basically, it's just a ratio between this tensor spectrum and the scalar spectrum. And the reason they do that is because we have measured the scalar spectrum. We know what this is just 10 to the minus 10. Yeah? So this is an equally good measure of the tensor amplitude. Just some different relative normalization. But when you do that and look at the final expressions that I got for these 2 power spectra, you find that this will look like 8. So 8 over M Planck, this different normalization. And then phi, this derivative of phi with respect to the number of e-folds. So dn is defined as just h dt or d logarithm of a. Yeah? So somehow this tensor to scalar ratio depends on the evolution of the inflaton field, with respect to e-fold, or just a different measure of time. Yeah? And for example, what you can do is you can just integrate this expression over the whole period of inflation that we observe. So there's this integral relation. If you integrate from the end of inflation to the time when C and B fluctuations were created, this, yeah? And if you massage it a little bit, do some approximate. The problem is that this R can be evolving with time. Yeah? So here I define it as a function of k, so as a function of, for different time, horizon exits, we'll get slightly different values. But for slow roll inflation, for example, that evolution is suppressed. It's second order in slow roll. So if you assume this were constant and you say this is approximately 60 E-folds between the end of inflation and CMB scales, something like this, you get an approximate relation where there's some order, slightly model-dependent order 1 coefficient, and then R divided by 0.01 to the 1/2. Yeah. So what that means is whenever this quantity R is bigger than, whenever the scalar amplitude is bigger than 1%, yeah, the field moved over a distance which is bigger than m Planck. And this is something we already saw in the first lecture, when we looked at m squared, phi squared inflation. And we found that the field has to start at 15 times m Planck. But this is, even without specifying the potential. And it's just looking at these power spectra, dividing them and doing this integral. So this is what the light bond is. And curiously enough, so the current constraint on R, so the current constraint is something like, slightly dependent on what you're looking at, is below 30%. And so in the near future, maybe in the next 10 years or so, what we can realistically hope to get down to is actually this level. It's just a numerical coincidence. It didn't have to be that way necessarily. What just so happens is that this is something that we will probably probe pretty soonish. And it happens to coincide with something that smells quantum gravity-likey. So next time I'm going to talk about the implication, what it would mean if we do observe tensors, then it means the field moved over a large distance.
Is this during inflation, the delta psi?
So it's
Or is it between the inflation and the...
CMB scales. Yeah, so if I were to plot my spectrum, my potential, yeah. So CMB or large scales were created earlier during inflation. And then the end of inflation was here. So that's this distance. And notice actually this is the minimal distance that the field had to move. If there's some extra E-folds beyond the CMB scale, because inflation had to start before that, and it could have started way before that, then you would have to add extra E-folds. Yeah? And sometimes what people do, if they don't want to do this order 1 business, then what they say is that, you're just looking at 4 E-folds in the CMB directly. And then, so rather than doing an integral over 60 E-folds, they say over 4 E-folds really R is not changing. And then, this is an even better approximation, and you get something which is slightly weaker. Because instead of, basically it's weaker by a ratio of 4 over 60 or something. So if you want to be conservative, you say just during the time when CMB scales were created, the field moved over a small distance. What is that distance relative to R? Yeah? Well, we know that, and then that's written as an inequality, because we know there had to be more before and after that time. Yeah? Okay. Yeah. Yes and no. So it depends what you mean by a multi-field. Yeah. So if you mean by multi-field, if it makes an assumption that actually the inflaton field is the same field that drives inflation and creates the fluctuations. If you have a second field that creates the fluctuations, you decouple things. And there's some cases where this still survives, and in some cases where this is weakened. It also makes an assumption here that you're using canonical kinetic term. Next lecture, I'm going to talk about non-Gaussianities, and I'm going to talk about having non-trivial, dBi action type kinetic terms. And it turns out for dBi, actually, this is precisely preserved by a coincidence in what these kinetic terms look like. But for arbitrary kinetic terms, you can actually have a change here. But usually, the change goes in the opposite way, typically. Well, we're going to talk about it maybe. but it's kind of a hot topic. So for example, in string theory, when people are trying to construct inflation models, they often, for large field, this is then called large field inflation, they run into the problem of how do they preserve the potential over such a large distance in field space. Typically, so they effective field theory arguments where you expect that the potential decorrelates over a much shorter distance. It has structure over much shorter distance scales. So this is one of the challenges that you didn't have to face. And it follows from the simple argument. And so one final thing I should say, so one reason tensors are so powerful, so I should say scalars, of course, we have seen, tensors we haven't seen, and I'm going to tell you how we propose to see tensors. But one of the reasons tensors are so powerful is that the power spectrum here only depends on h. Whereas here you have this degeneracy between h and epsilon. If you see tensors, it immediately tells you what was h during inflation. And h is directly related to the energy scale of inflation. So with one sweep, it gives you like one piece of information that you know, should be number one on your wish list if you want to know something about inflation. It's the energy scale. And so tensor to scalar ratio value is bigger than 0.01, basically corresponds to God's scale inflation. If the tensor scalar ratio is much lower, then you have to contemplate, lower scale inflation models.
So now what are the bounds on H?
On what?
On H during inflation.
On H during inflation, as an energy scale? Okay, let me write it. So you can actually, if you use the scalar normalization, you can write the energy scale of inflation in terms of this, no, not H, but V, as something like this, where, okay, this should be twiddle. So you could work this out exactly for yourself. Yeah, if you just also here, this 10 to the minus 10 is not exact. We actually know this to some, high precision. Yeah, you can put some error bars there. So you then can get something that scales like this. The problem is actually one of the problems is it scales with the 1/4 root of this tensor to scalar ratio, which is unfortunate. Yeah. So you can change the tensor to scalar ratio by quite a bit. And that's actually what experiments are sensitive to. It's this tensor to scalar ratio. You change it by quite a bit, and the energy scale still stays high. So to say that inflation is high scale when it's above 1% tensor to scalar ratio and low scale below, is kind of a fake because this is 1/4 root. It doesn't really change much when you change R. So you really have to decrease this tensor to scalar ratio by quite a lot. Yeah. For example, 4 orders of magnitude to make 1 order of magnitude energy scale decrease. Yeah. So that's something that I should mention. Yeah.
So H, maybe I just look at this quality I can get that H is equivalent to 15 GeV, something like that. There is in the blank square separation, right?
Okay, yeah. Well.
So this is the scale of inflation, or I can get much less than.
Well, usually what people mean is the scale of inflation. They mean this V here. Yeah. So so H squared is 1/3 and Planck squared V. So there's an Planck conversion. So in Planck, things. If you would typically assess the energy scale of inflation with V, and then H would be more something like the inflaton mass, and it won't have the same value. It would typically be lower. But it's also, later, next time we're going to talk about, it's also the scale where you should put the cutoff of your effective theory, you should put at least H. So it's actually physically relevant in terms of your effective field theory description of inflation. But, okay, so I have much more to say, so I want to carry on. Okay, so let me talk a little bit about the scale dependence of these power spectra. So the reason they depend on K, I explained, was because you evaluate this at horizon crossing. And then what you do, so as a cosmologist, somebody last week told me simple steps for simple people or something, or so just simplest thing you can think of is power law, yeah, and it's pretty good actually because CMB scales are a pretty narrow range, especially in field space for the inflaton. You're basically evaluating this, and so you could normalize this with respect to some reference scale, k star. That's often called the pivot scale. And so you ask, what's the slope of this power spectrum around a particular point in k space? And then you can do, you can say, oh, maybe there's some, this can depend on k and so on. And okay, but so let's just try the simplest idea. You have a constant deviation from scale invariance. So scale invariance would correspond to ns of 1 and nt of 0. And the reason that they defined, ns minus 1 and nt 0 is just unfortunate. Yeah, but and I'm actually not old enough to know the history why this is, but yeah. Okay, so then one way, an equivalent definition would be to say it's just the logarithmic derivative of this power spectrum with respect to ln k, yeah, and then something similar for nt. And so this derivative I can split up into two factors. Derivative with respect to number of e-folds times e-folds. Yeah. Okay, so then let's look at these two factors separately. So this first factor is then, so if you remember, this guy here was proportional to h squared over epsilon. So I can write this as two terms, one just 2 d ln h dn, and the second one d ln epsilon dn. Okay? So if you go way back to the first lecture, I think I was expressing this lower order parameters in terms of derivatives of the log, the fractional change of the Hubble parameter, the fractional change of epsilon with respect to the number of e-folds. Yeah? So if you look up those definitions, you can write this as twice eta minus 4 times epsilon. Yeah? So there are minus 2 epsilons coming from here. There's a 2 eta and another minus 2 epsilons coming from this term. Yeah? So you see that this ns minus 1 is proportional to some particular linear combination of these slow roll parameters. So then for inflation, we typically expect that this is less than 1. Yeah? And in specific models, you will find that this should be of order 1%, give or take a factor of a few. Yeah? So inflation predicts that it should be nearly scale invariant, but it also tells you that there should be some deviation from scale invariant at the percent level. And that's one of the first things after you measure the amplitude of scalar fluctuations is to check whether that scale invariance, first of all, is really true to 0th order approximations, and then check this first order result where you expect 1% deviation. Yeah? Sorry, in order for this to be completely true, you have to prove that this one is approximately 1. And I leave that as an exercise for you. This is actually 1 plus epsilon. And the way you do that is you use the horizon crossing condition, which is KAH. Yeah? And so take the logarithm of those, you get ln k equals n plus ln h. And now if you take derivatives with respect to n, you get 1 here, you get some epsilon here, yeah? And then you just take the inverse. And so that's how you get 1 plus epsilon. And this epsilon is small, so it's just 1, so it won't affect, it's only a second order correction to this result. Yeah? Okay, and you could do the same thing for nt, and let me put it here. So if you do the same thing for nt, you find that it's approximately 1 minus 2 epsilon. Yeah? And so effectively, it only has this term because it only depends on h. There's no dependence on this conversion with epsilon. And that's why it just has minus 2 epsilon coming from this first guy. Yeah? And you could also, from this definition, you could also compute the tensor to scalar ratio in terms of these slow roll parameters. And
so basically measuring the scalar and tensor power spectrum precisely would allow us to nail down the inflation slow roll parameters, right?
so I'm going to tell you what do you measure. So So ns minus 1, let's just collect those. Ns minus 1 is 2 epsilon minus 4 eta. Nt was minus 2 epsilon. R is 16 epsilon. Yeah? Sorry? Yeah, sorry. This, yeah? So by measuring those three things, you could disentangle, basically measure, eta and epsilon. This one, realistically, we don't have a shot at measuring even, for a good while. So typically what people just consider is, those two, say. And then also the amplitude of scalar fluctuations, which we know is 10 to the minus 10. Yeah? And so this is under the assumption that you have a single field slow roll canonical kinetic term, and then those measurements will actually tell you something about the shape of the potential. Yeah? So from those things together, you reconstruct basically the first two derivatives of the potential and also the height of the potential, I think. Yeah. So there's this program called potential reconstruction. Okay. People sometimes get very excited about knowing the v prime and v double prime of the potential. Personally, I tend to be less excited because what does it? Actually, those three would be pretty interesting. But then also you can go on and actually measure deviations from this, and then you get triple prime of the potential. What is not clear, for a particle physicist, if I tell you v triple prime of the inflationary potential, well, you wouldn't change your life. Okay. So I'm going to skip one thing and just leave it for you to do, which is if you just take, again, our favorite m squared phi squared, and compute epsilon and eta, yeah? Go to the CMB scale, yeah? So and evaluate those basically at 60 e-folds before the end. And then plug it back in here, then find out what the predictions would be for m squared phi squared. Yeah? So you would find for ns, you find something like 0.96. Or parametrically, it's going to be 2 divided by the number of e-folds to the CMB scale. And this R is going to be roughly 0.1, maybe 0.16. I mean, you figure out exactly. Yeah? So this is very simple. Last time we already calculated number of the e-folds in terms of phi. So rho parameters in terms of phi. You can just invert those and get those predictions. And one thing you find is when you use this scalar amplitude, you will find that this requires that you choose the mass in m squared phi squared to be 10 to the minus 6 times the Planck mass. Yeah? But that way we almost did the complete calculation for m squared phi squared. Yeah? We did the slow roll analysis, and then now we calculated the fluctuations for m squared phi squared and get those predictions. Yeah? Okay, so then next what I want to talk about is how we actually extract those predictions from observations. How we go from something that has this complicated shape to something that we hope is nearly scale invariant. Yeah? Okay, so I want to talk about how to go to observation. To observations. So schematically, so you have some observable Q that can depend on wave number, and it can depend on time, the time when you're making the measurement. And you want to relate this observable to our primordial R evaluated at tau star. And by tau star, I mean horizon crossing, yeah? And so in order to do this, I have to put what's called a transfer function in here that can depend on k, tau, tau star. Okay? And so the transfer function captures a couple of things. One, for example, it captures how to relate in the first place, a curvature perturbation into a temperature perturbation. Just there could be some just physical transformation. Then it captures, if there's any sub-horizon evolution, it can capture that there are projection effects. So a lot of things, go into this transfer function. I'm going to actually write out for you what these expressions look like for the CMB, for example. But effectively, we're going to treat this as a black box where this is some known physics. And the reason I can treat this as known physics was exactly this, because I was choosing this variable that re-entered the horizon at later times, and I didn't have to worry. During a time when the universe was in a very high energy state, this mode was actually outside the horizon, and I'm arguing that it's constant outside the horizon. If I had chose a different quantity, then I would have been obliged to include that evolution in the transfer function, but I might be not so certain about what the actual physics is at the gut scale, or anywhere between TeV and gut. So this is known physics. This is maybe unknown physics, the physics of inflation. And this is basically what we measure in experiment. So then the inverse problem is we measure this, we want to infer this, so we use these transfer functions that we can compute using just fluid dynamics, GR, atomic physics, things that we think we understand. And in particular, things that we have tested in the lab. Okay. So that's the basic idea. So let me describe, I want to describe two observables that we have. Yeah? And so you heard about those before. The two observables, the two Qs that we have are the CMB and then the large-scale structure. So I know you have seen this before, so I write this out quickly. So the CMB usually is viewed as a projection on the sky. This n here is a unit vector pointing to the direction in the sky. And so then you expand this in spherical harmonics. Yeah. And then from these harmonics, you can define like a rotationally invariant angular power spectrum. So you sum over the M modes, and that's because of isotropy of the background. We can redo this. And so this is then expressed as, in terms of this correlation function here. And this is then typically what we plot when we look at these CMB power spectra. Well, actually, what's plotted when you see this plateau here is actually this combination L times L plus 1 CL. And we can talk later about why you choose this extra factor. Has to do with projection. Okay, and then so for the CMB, the transfer function is actually imposed onto these ALMs directly. Yeah? So you can write ALM as, okay, there's some factors that don't matter much. And then there's a k-space integral. Okay, so then here there's a first mystery object. Then there's another YLM in k-space. And then so here's our primordial curvature perturbation. Yeah? And so this is a transfer function which can be written as an integral over time of some source function. Okay, bear with me. I will explain these different things. Okay, but that's it. Yeah. So this is a physical source, and this is a projection function So you can think of this as just linear combinations of Bessel functions or something. That just depends on how the geometry works out when you project the different modes. This source function is depends on kind of the plasma recombination, things like this. It also has the conversion of how to go from a curvature perturbation to a temperature perturbation. And then this, so this really combines, this is just equal. This combines into this function. And there are differential equations actually for this, couple of differential equations that you can solve. So all of this shouldn't matter too much to you because it's done by magic or CMB fast. Yeah? So there's this computer program. If you look into the program, you will see it will do these integrals for you. And it will actually solve for these. It will tell you these source functions will be explicitly defined in terms of for the electron density, metric perturbations, things like this. All of this goes in, and then it just, at the end, it's a transfer function that relates curvature perturbation to ALMs. Yeah? But you can take this expression now and plug it in here, and then get, again, some pi factor, now an integral over k, the power spectrum of R, and then 2 of these transfers. And so the T here denotes that this is a transfer function specific to temperature fluctuations. Yeah? Later we're also going to talk about polarization, and the transfer functions will be slightly different because polarization is generated in a certain way. Yeah? Okay, so if you don't care much for these details, you can just go to this final answer. And all I meant to say here is that you have this primordial initial value for the power spectrum. You have these 2 transfer functions which are computed by some known physics. You do this integral and you get the observed CL power spectrum. Yeah? And in fact, for this regime, I'm not going to write it out, but if you look at my notes, for this regime, for large angles, yeah, small L values, these transfer functions actually become very simple and analytic, just a simple Bessel function. Because there's no real sub-horizon physics that is affecting those scales. And so all of the effect boils down to like just a projection effect that is purely geometrical. And so it can be written down analytically, and you can actually solve for this. Yeah, so in the notes you will see the analytic solution valid on these large scales. Good. Okay, but so this transfer expression is exactly what I mean by going from this CL power spectrum to basically delta S of K, looking something like this. It would be exactly flat if NS was equal to 1. So this is K. It would be, if NS was bigger than 1, it would be sloped like this. If NS was less than 1, it's sloped the other way. Yeah? So by making this, by solving this inverse problem, we basically can create, plots like this effectively, with error bars, and then measure off what the scale dependence of the power spectrum is, what its amplitude is, and things like this. So let me tell you what then the data tells you. So when you study WMAP 5 years, combine it with other stuff. So baryon acoustic oscillations, supernova, large-scale structure, which I haven't talked about yet. If you do that, you get an NS value which is 0.96, plus, okay, error bars mean much less to theorists than they should. There's a 13, I remember, but I think there's a 0 first. Something like this. Okay?
Aren't there any ambiguities when we solve for the inverse problem?
Yeah, so there can be degeneracies, for example, with other cosmological parameters. So this NS one, Marlena might help me out, but this NS one I think is degenerate with tau, for example. The optical depth to reionization is also degenerate actually with the tensor to scalar ratio. So when you're trying to constrain both at the same time, you get some confidence contours that look like this, whereas this would be n is equal to 1. Yeah? This edge here would correspond to roughly 0.3, I guess. Yeah? So these are 1 and 2 sigma contours for these experiments. So you see this degeneracy by making R large, you can make NS further towards the blue and things like this. And you can think about why that happens. When you make R larger, you add some tensor power, and it will change the large scale slope of the CMB spectrum. Yeah.
So for all these combined experiments with data, is there any particular experiment that's creating a large draw away from
Yeah. But I'm not sure if I remember. So actually for this NS1, even W map by itself is pretty good, I think. And then usually when you do W map plus baryon oscillation, you almost already to the other things don't add much. But I'm not a great expert on these things. I read it and forget it and read it and forget it. But that's why I actually wrote it up, I think. I probably told you some of these degeneracies. Maybe not. Okay. Sorry? NS? No, because remember how this NS was 1 plus 2 eta minus 4 epsilon? You can start playing games now, because you have these two parameters, and just by, Huh? They're small, but they can have either sign. Yeah, so the prediction, yeah, it's true. The prediction is that it's nearly scale invariant, so that's good news already. The fact that we see something like this at the 0th order approximation rather than something crazy, yeah, is already good. It's telling you if the fluctuation were created by something like inflation, the energy density was changing h dot. No, this alone I think wouldn't be enough. That's why you'd like to see tensors and something.
If you measure at R, it's particular value.
R?
If you saw R,
yeah.
some value, then would that be a confirmation of inflation?
I think most people, I personally would think so, yes. Some people would think this is already, yeah, if you're a diehard believer, then inflation is already. I'm going to actually talk about something very curious that is much more qualitative, that the fact that we actually see superhorizon coherent fluctuations at the recombination. We actually see those. And so that's much more striking even than just this value of the, yeah? And so that's something that is not so often mentioned because it's a little bit harder to explain, but it's a qualitative thing that we literally see that some mechanism has created those fluctuations on superhorizon scales at recombination. Yeah? So if you believe in causality, then that's something that's puzzling if you don't have some prior phase, some negative tau business like inflation.
So what you said, what you said just there is kind of similar to the horizon problem, right? Because
sure.
The horizon problem is like the 0th order correlation with
Yeah.
You're basically saying there's higher correlation as well on superhorizon scales, just like the monopole, and everything kind of works out in that way.
True. Yeah. Well, the solution to the horizon problem is related to the fact that you have these superhorizon fluctuations because you have a shrink. The way we solved the horizon problems in the simplest version was we arranged that the co-moving Hubble radius was decreasing. Yeah? And because it was decreasing, you could have these fluctuations that were subhorizon before inflation, and then. But there's something. The coherence is also interesting. The reason that you see these oscillations and you don't see something that is, yeah, this is actually an interference effect where the phases of the different Fourier modes were actually all created in phase, in sync, in some sense. Yeah, and that has to do with superhorizon freezing. So I'm going to come to. If not, we talk about it over lunch or something. And that has to do with this fact that this zeta, this r dot is 0 outside the horizon, and when it comes back into the horizon, it starts with 0 velocity, with a particular phase. Any Fourier mode with the same k starts with the same phase, and then there are many different Fourier modes with same k that effectively interfere to produce this spectrum. So the fact that you see these oscillations is also telling you something. Yeah.
Information of the R, right? That means ratio. Like in what sense? Can you not explain
how you get information on R? Yeah, so at the moment, actually, this limit on R is mainly coming just from measuring temperature. fluctuations. Yeah. So probably not this time, but next time I'm also going to tell if you measure the polarization of the CMB, not just the temperature fluctuations. Yeah, then there's actually a very sensitive probe that only depends on R, nothing else. Yeah? So there's a particular polarization state. So you can decompose the polarization into two different modes. And there's one mode that is only sourced by tensors. If you see that mode in the sky, that's, some people call it smoking gun, signature of such gravity waves. So that would be a much better measure of. Then you see R see R directly. But here you just R also has an effect on the temperature spectrum because it carries power. So but it sources these temperature fluctuations in a different way. Yeah. So I thought there was an easy answer, but I'm realizing it's not quite so easy. But there's if we have more than 10 minutes later, we can talk about it. There is an easy way of just. At the moment, you're saying?
Yeah.
Yeah, because at the moment we're not measuring this polarization mode that I'm talking about very accurately.
Yeah, right.
So we only have upper limits, and there are foreground signals coming from our galaxy that are actually much bigger than what inflation we think inflation could produce. And so we have to understand at the moment we're in the process actually of understanding the other crap. And so there's this inverse problem. There's another problem that you have to really make sure that you're seeing something that is early universe rather than late our galaxy, which is interesting for some people. But
will we be able to do that with the Planck data?
Yeah, so Planck is not, with Planck, I don't know, I don't want to talk out of. So with Planck, roughly, I think you get down to R's of, a little bit better than point. Planck is not optimized for these polarization measurements. Yeah? So what it will do very well actually is do this NS. Because Planck will actually measure the temperature power spectrum up to very, very large L. And basically, in order to get an accurate number for NS, you want to have a large lever arm. You want to measure things over a large enough scale so that you have statistical power on this slope. So that's what it will do, but it won't. The tensors.
Is there a mission plan to measure that?
Yeah. Okay. I'll give you one shameless piece of self-promotion, but that's going to be my only one. So there's this thing called CMB pole. And so last year, I think 60 of us wrote this proposal for, I'm not sure, or a white paper or whatever what it's called. So there's on the arXiv, I have it, I think in my notes I give you the reference. There's like this 100-page thing where we describe basically what polarization can do, all these observations, how you constrain inflation. And the idea is that you do that with a satellite experiment. This would be the ultimate CMB satellite experiment, where that is optimized for measuring these, what's called B modes. Okay, and this CMB pole is also called EPIC, Experimental Probe of Inflationary Cosmology. So at the moment, there's just a 1-year funding to discuss whether this could ever work. Once then funding would be granted, then it transforms into something that's called EPIC. Okay. But what we wrote here is by itself actually a pretty good review, actually up-to-date review of inflation. So we use it as an excuse to write about inflation rather than. So yeah, you won't find much about it. There's another one that tells you how the experiment works. We say nothing about the experiments because we don't know anything, but we talk about the theory part. Yeah.
So on the notes you got it's for NS, and R, and then also this alpha S parameter.
Yes. Yeah. So alpha S, if you want, is what's called the running of the spectrum, and that's what I was saying. If you don't assume that NS is constant, but it changes as you go away from this pivot scale. Then I think one way of defining alpha S is to say you do an expansion in log k. So alpha S times ln k over the reference scale, I think. And so then you have a second parameter that constrains how you deviate from a fixed, constant tilt that doesn't change with k. And if you can compute this in slow roll, and it will depend, you have to do it to second order in slow roll parameter. Alpha s is actually 0 at first order in slow roll. And you compute it, and you get something which is epsilon squared, eta times epsilon, things like this. So then just judging by the magnitude of epsilon eta for slow roll, you expect this alpha s to be 10 to the minus 3 or something like that, something smaller. Sorry? You're asking whether it is the correct formula? Or?
Yeah, I'm just wondering if you just wrote that there, or if it's actually...
Oh, no, this is in the exponent.
Okay.
But check my notes if this is exactly. Maybe there's a factor of a half, or I don't know.
So does the fact that n is smaller than 1
Tells us something?
Yeah,
Yeah, for example, so say you look at the limit where r is very small. Yeah. So remember that, okay, at the expressions for ns, 1 plus 2 eta minus 4 epsilon, and r was 16 epsilon. Yeah. If you constrain yourself to models where r is subdominant, say we were waiting another while and we really don't see an r, and since there's a factor of 16, that would then tell us that epsilon is pretty small. And then if epsilon is pretty small, then all of this effect on ns is coming from eta. And eta is related to the curvature of the potential, the second derivative. So we'll tell you something about the sign of the Imstadt mass in some sense, whether it's positive or negative. Yeah? So whether you're rolling off a hill or you're rolling towards a minimum, something like this. Any other question? Okay, so let me then spend 5 minutes actually describing these E and B polarization modes, and then I'm going to move the rest to next time. Okay, so there's a simple picture to explain how polarization is created in the CMB. Yeah? So if you look at, let me draw the picture and then explain it. So imagine you have a single free electron, yeah? And then you have two radiation coming from two orthogonal directions. And later you could integrate over the whole, over some sphere. But okay, just looking at these two orthogonal directions, and actually, and two polarization modes. And so let's say this is a hot spot, and this is a cold spot. Okay. Then just thinking about how these different polarization modes get scattered by the electron, you will find that of these two polarization modes, only this one will be survive the scattering. Basically, this one will just. I should have drawn this I think this way. Doesn't really, yeah. So this, as far as these two polarizations are concerned, this Thomson scattering of the electron acts like a polarizer. So it produces one linear polarization mode. But then you have the second direction. Okay, you should look at my notes. This picture is a little bit screwed up. Anyway, so the second one will let the second polarization mode through. If those two spots were exactly the same temperature, then what you get out is still something that is unpolarized. Yeah, so just for isotropic and homogeneous radiation, when they scatter from all directions at a single electron, doesn't produce polarization. Yeah? But now we know that the CMB isn't isotropic. We have actually seen these temperature fluctuations. So those temperature fluctuations at last scattering get converted into polarization when they scatter from free electrons. So that's the process, because then this hot spot has more intensity than this cold one. So you get an effective polarization which is dominant in one direction. Yeah? Okay? And so the main reason why polarization is powerful is because, so it's not a scalar, so it's a rank 2 tensor field, not quite a vector, of course, because it doesn't have direction. So it's a rank 2 tensor, and so it has more information in principle than just the scalar temperature fluctuations. And one of these ways of exploiting that information is by decomposing the pattern of polarization into E modes and B modes. So E modes are when you look at the sky and you see patterns that look. So in my notes I give you a mathematical way of defining those, but like in pictures, it's basically you look at polarization directions and you see a pattern that has no curl component. Yeah. If you were to take the curl of that field, you get 0, and so that's just like an electromagnetism where the E field is curl free, and so that's why it's called E. And those two patterns are just different signs of the E and B modes. So this would be negative, this would be positive. And then there are different types of patterns. This looks almost like this. What I mean to draw here is something that has is divergence free but has a curl. So yeah, well, there's a picture in my notes, yeah? So I'm not an artist. And one thing to note is, for example, the E modes are symmetric on the reflection. If I draw a mirror plane through the axis, then if I reflect it, this doesn't change, whereas the B modes change on the reflection. Yeah? And so those symmetry properties actually affect whether correlations exist between B and T, between B mode polarization and temperature or not, and so on. So in particular, what you find is that the power spectrum of B and T, for example, and B and E, we expect to be identically 0, yeah? Unless parity is violated in the early universe. Yeah? So this is by parity conservation. This should be 0, but we have these other correlation functions where we have TT, TE, EE, and then the autocorrelation of B modes. Yeah? And so the crucial point that I'm going to talk more about next time is that this guy is not produced by scalars. Yeah? Everything else is sourced by both scalars and tensors. But this B mode correlation, just by symmetry, you can show by symmetry, is not produced by scalars. Yeah? So if you were to see a signal in a pattern on the sky that looks nicer than what I draw, but like effectively like this, yeah, you could calculate its power spectrum, and from the amplitude of the power spectrum, you would actually infer what this tensor to scalar parameter R is. So this is really what these experiments are proposals. C and bipolar, are gunning for. Measuring this particular polarization pattern and finding out what its amplitude is. So maybe let us stop here.
Okay, quick announcement, everyone.